স্যার বলছি যে একটা জিনিস
হ্যাঁ
প্রশ্ন,
বলো
স্যার
বলো।
সেই অ্যাডভান্স মেকানিক্স এর জন্য কি স্যার ম্যাথমেটিক্স এর কি মানে টেন্সার বা কিছু লিনিয়ার অ্যালজেব্রা গুলো করতে লাগবে?
মানে আমরা আমরা যেটা করছি এখন,
হ্যাঁ হ্যাঁ হ্যাঁ,
না না এটার জন্য টেনসার ফেন্সার এখন কিছু লাগবে না।
ঠিক আছে ঠিক আছে
যেটুকু লাগবে সেটুকু আমি বলে দেবো।
ঠিক
ঠিক আছে। আচ্ছা, তো আমরা, so as we see that we will be going to take up the new chapter today, that is what is termed as the, you know, the virtual work. So in the virtual work session, so our textbook that we will follow as usual will be Merriam and Craig, but this time we will be referring to the statics book, because virtual work is normally, you know, a very powerful method which is generally applied in case of statics. Although we will have a small application of the virtual work in the dynamics as well, so we will see. So mainly in this virtual work chapter, our main focus will be to consider the equilibrium, statical equilibrium of the bodies, and little bit of dynamics problems as well we need to take up, where we will show the application of the virtual work method. Apart from these, there are other methods of virtual work in mechanics of materials also. That means in strength of materials also there is a scope of, you know, utilizing the principle of virtual work. But there we don't have to actually, you know, explicitly apply the virtual work method. Rather, what we do, we formulate some energy principles in mechanics of materials using the concept of virtual work. So that is why we are actually not going in to discuss the method of virtual works application in mechanics of materials or mechanics of deformable bodies. So mainly here our objective of, you know, studying this method of virtual work will be limited to the problems of rigid body mechanics. I mean, it will be divided in statics as well as it will be considered in little bit of dynamics. So therefore, let's start with the, you know, the statics portion. This is Merriam Craig's book of statics, the book which is widely available in the internet. So you can download this book and take up the problem from there, just like you did for the case of dynamics. Or if you have the print copy of this book, there is no problem, there is no need to download it, and you can have the situation. Now, this method of virtual work, as I have told you, will be mainly, you know, focused to the statics problem. So before going into that, let us quickly review the concept of work. This is actually known to you, so I'll not be very much elaborating on this part. But those who want to refresh your concepts of work can please go through it from the book. So as you know that the work, you know, this is the body which is under the condition of rest, and we have some force that is acting on it. And because of the application of this force which is acting on it, which was otherwise conditioned at the condition of rest, now because of the application of this force, the body has suffered a displacement. So this displacement, which is represented by delta S, is actually termed as the real displacement. This displacement is real displacement in the sense that you can physically see this displacement, and it requires certain time that this body from this configuration A, it will come to the configuration A prime. So it will require certain time during which this overall displacement of the body will take place. Now, while doing it, so we know that this is what is termed as the work done. Actually, this is the work done over this infinitesimally small displacement. So sometimes this work done can be written as capital U, or sometimes, you know, it is written as du, that is the differential work done by the force. So we see that it is written by the definition, the work done by the force F bar on the body during this displacement is given by this. This is already known to us. So we see that you can decompose this F cos alpha can say this is the component of the force F cos alpha, this is the component of the force F cos alpha in the direction of the displacement. This way you can view it, writing it in the bracketed term this way. Else what you can do, you can take the component of this displacement in the direction of the force and take this as delta S cos alpha, and thereby you can take up the work done from there. Now, if the force is having some other angle with the direction of the displacement, this work will be preceded with a negative sign. For example, in this situation where we have this case. Now, in this type of definition, what you see from here is this, that the body is moving along a straight line path, or so to say, the body is having some rectilinear displacement. But for a more general case, when the body is moving along a curved path, we see that how we can define this work done over this small interval of displacement. Now that will be given by the change of the position vector of the particle at the two different locations, and that differential increment of the position vector is considered as dr bar, and the work is calculated by this scalar product of the two vectors f bar dot dr bar, and this is du in the sense that since this is the very differential change in the position vector, the work function will be also differentially small, and we can write it in this way. So this is how we can see it. Now you can express the whole thing in the vector format. If I express the force function in the three components vectorially, as well as the displacement dr bar, which is actually the change in the position vector from the point A to point A prime, we can therefore say that this is represented by this, and the work done, the differential change in the work done can be given by this. Now this is what is called the differential definition of the work done. You can of course integrate the above equations for a finite change in the position of the particle. That means suppose this particle is initially at the position A1, and after certain time it goes to this position A2, which I call it to be the final position over this window. It may not be truly absolutely final position. I mean to say that the body may continue beyond this position also while moving along this curved path. But in this window, I can say this is my initial position of the particle, and this is called as the final position of the particle. So within this initial final window, if I integrate this equation, correct, between these two limits, I will be getting the total work done by the force F bar while, moving this particle from this current position to this final position. So this is the work done. Now in a similar, this is actually what is called as the work done by a force. Now in a similar manner, we can calculate the work done by a couple. How we can do it? Now this, you see, this is the body, for example, and because of this application of the couple M bar or the moment M bar, the body has, is displaced like this. So the difference between this type of displacement geometry of the body with the earlier displacement is that, first of all, the body is represented here as a particle. So there is no question of considering the change of orientation of the body as it is moving or is suffering its displacement from one position to another position. So in this case, when we are having a translational kind of movement, there we may ignore the physical dimension of the body, because we see that there is no, really speaking, there is no change in orientation of the body. However, in case of translational motion, this may be true, but in case of rotational motion, it is not true. For example, in this case, if we have, this is a rigid body, and on this rigid body, we are applying this couple. So because of that, the rigid body is, changing its displacement, and it goes into this position, which shows that there is some change in the orientation of this rigid body, which was otherwise absent in case of particle assumption of the work done that is being calculated by the different forces. So this orientation change of this, the rigid body is measured by this angle called d theta, which shows the angle between the two successive, positions. Now, while doing this is, it's a very small change we have considered. So let us first actually try to calculate for this very small change of the orientation of the body, what is the work done by this couple. So in order to do it, let us actually, divide this couple by the two equal and opposite forces, because we know that we can always divide this couple into equivalent system. So this is basically the equivalent system of the couple that is shown. So I take a point A and take a point B on the body. These 2 points are taken suitably at a distance of B apart from each other, and we imagine that there are two perpendicular but opposite parallel forces which are acting on the body like this. And because of the initial geometry changes to this as a final geometry over this d theta interval, the final geometry is shown by this dotted line for this differentially small increment of the change in orientation of the body. We find that the particle A goes to the position A prime and particle B goes to the position B prime. So A prime and B prime basically belong to this changed geometry of the body, which is the changed orientation because of the application of this couple. Now, this displacement, which are shown like this dr, this displacement, that is A prime and B prime. So you see from here, actually it, sorry, I just made a mistake. Let us see that the final position of the particle A is not A prime, rather it is A double prime. And this is B is to B prime. So this A double prime and B prime, they belong to the final geometry of the body. I said that it is A prime, B prime, it is not correct. So it is A double prime, B prime are the final positions respectively for the point A and point B in the changed geometry. Now we can achieve this final position in two ways. First of all, we can give a displacement, I mean to say we can give a translational motion to this body, and because of that translational motion, the point B reaches to its final position B prime. Remember I said that A double prime and B prime are the final positions of these 2 points A and B in the changed geometry. So as a result, what we give, we first give a translation such that the point B directly comes to its final position, and correspondingly the point A goes to the position A prime. So naturally this is a translational motion. So either of this A and B will suffer the same displacement vector. So you see dr bar B and dr bar B both will be same because it is translational motion. But as you see that this is not the final position of A. The final position of A is A double prime. Therefore, what we need to do, but we have already reached B prime, the final position. So in order to reach the point A, take the point A prime to A double prime, while B has already come to its original position, or rather final position. So what we do, we give the rotation of this body with respect to the point B prime, because we do not need any further movement of B prime, because we have already reached the final position of point B, but we haven't reached the final position for point A. So in order to have this, so this is A prime is the intermediate position of the point A as it suffers this change in configuration. So what we do, therefore, keeping this as the center, we give the rotation so that the point A prime moves to A double prime. So therefore, we find from here that the final configuration of the body is reached as a combination of translation and rotation. This is basically the fundamental principle of Chesel's theorem, which is known as Chesel's theorem in mechanics, which shows that any the displacement, general displacement of a body can be basically thought of as a combination of translational motion plus the rotational motion. So in this case, we have opted for the displacement, initial translation. We have opted for the case when I just considered the final position of point B and we straight away move to that final position by giving the initial translational motion. Instead, one can also select the final position of A to A double prime as well. That means in that case, he or she would have given the final initial translational motion such that A directly goes to A double prime and B goes to some intermediate position where B is supposed to, here. So A is going over there and B naturally following the parallelogram, it will be somewhere here. So that will be considered as B prime. But since this is not the final position of B, the final position of B is here. So what you need to do, you now need to rotate the body with respect to this final position of point A so that the point B from its intermediate position can come to the final position. So either way you can do it, but your result will be remaining the same. So idea is therefore the entire span of the change of configuration is considered to be the sum of some translational motion and some rotational motion. Either translational motion can be selected for any of the points. For example, in this illustration, we have chosen the translational motion such that the point B directly goes to its final position, while the point A is not. It will accordingly move to some intermediate position. And then giving the rotation of the body with respect to this final position of point B, we will be able to bring the intermediate position of point A to its final position. So either you can do it in this manner or you can take it directly so that A goes to its final position directly due to the translational motion and B comes to some intermediate position. Then you would give the rotation about the point A double prime or the final position of the point A so that the intermediate position of point B gets transferred to its final position. So either way you can do this thing. Now you can very easily see from here that A double prime, this can be considered as almost perpendicular to this because this is a very small displacements. So you can see therefore for this overall travel, the work done by these two forces because of this translational motion will be 0. Why it is so? It is simply because the work done by the force F bar while the point A goes to the intermediate position A prime and the point B goes to its final position B prime, I find that the total work done by these two forces will be F bar dot dr bar B plus minus F bar dot dr bar B. Because this force and this force are opposite, so one is designated as F bar, so other will be designated as minus F bar. Anyone you can take it plus, then the other will be considered as minus. You can take this force as plus, then this will be then recognized as minus force. Correct? So in this case, therefore, we find that the actually the total work done for this translational motion, right, by these two coupled forces will be equal to 0 because the dr bar B and dr bar B, both these displacements are equal and same direction because of the translational nature of the initial displacement. So therefore this result will be 0. So now the force goes to this point. Now here, because of the rotation, the line of action of the force is not changing. Correct? So therefore the work done by the minus F bar force will be 0 here because it does not have any displacement, because we have already gone to the final position of B and then we are taking the rotation considering that final position of B as the center. So as a result, the force F minus F bar is immovable in the second part of my rotational motion. So therefore, this work done by this force will be 0 there. Then we are left with the work done by the force F bar. Now, since you see that this is perpendicular, I mean to say this dr bar, this b d theta, this vector, you know, it is perpendicular to AB prime, A dash B dash, sorry. That means it is also perpendicular to the direction AB. So it essentially means that this force F bar and this vector will be parallel with each other, because F bar is also perpendicular to AB. So it therefore shows that this F bar vector and this displacement vector will be parallel with respect to each other, and the work done will be thus given by how much? Now that will be equal to F bar dot, you know, this component. So you see, you need to select the two forces in such a way that the sense of the couple remains the same, because these are the equivalent forces, correct? So these are the equivalent forces, and because of that, the sense of this couple created by these two forces should be same as this moment vector. So as a result, one force will be like this and the other force will be like this. So here we find, therefore, then the total work done for this case, when I am bringing this body from this configuration to this configuration, therefore becomes equal to how much? Now that will be equal to magnitude of F multiplied by B d theta. Now F into B is nothing but the magnitude of the couple. So as ultimately what we find from here, that the work done is nothing but the magnitude of the couple multiplied by this angle of change in angle of orientation. So you see that since these two vectors are acting in the same sense, that means you are rotating it in this way. In this way means your body is essentially undergoing a rotation, clockwise rotation, as well as the couple is acting in the clockwise direction. So I have the positive work done by the couple. If it happens in such way that the orientation change is occurring along the anti-clockwise direction, while the couple is acting in the clockwise direction, therefore a minus sign would then come here in order to have that mismatch in the direction. So essentially we have that the work done by the couple, this is the differential work done, and for the finite change, you know, the work done is given by this thing. Now dimensions of work, this you already know that it should be joule. Now we, you know, once we see, this is a just quick recap of our work function, how we can calculate the work. Now we are coming to this concept of what is termed as the virtual work. Now what is actually meant by the virtual work? Then the work, you know, calculated, the work explained, the work function that is being explained so far in this article from here to the work done by the moment, whatever we discussed so far, that work we may call it as a real work, in the sense that this displacements or the change in the geometry of the configuration of the body or the system are real. That means they really take place and they take certain time to, you know, the achieve this change in the displacement or change in the configuration of the body. So in both ways we can call it to be the real kind of thing. Real means it essentially physically occurs, and you can observe this physical change of configuration, and accordingly we can calculate the work, or what is termed as the real work done by a force or real work done by a moment. But we never use this adjective called real. But now we have to use this concept of adjective called virtual work. And the virtual, it will be in the sense that our displacement, the displacement that we will be taking into consideration for our system, will be virtual in nature. That means these displacements in reality will never take place. It will take place in the mind of engineers. So in an hypothetical plane of reference, we consider a hypothetical displacement. and that hypothetical displacement takes place in no time. So it does not require any time. The body will not have any change in time. So there will be a sudden, the change in, this displacement or the change in configuration, and the entire change is considered to be virtual or hypothetical, and it will occur in the mind of engineers. So what it says, therefore, we now consider a particle whose static position is determined by forces which are acting on it. That means the particle is initially in static equilibrium. Any assumed and arbitrary small displacement delta r bar away from this natural position and consistent with the system constraints is called the virtual displacement. So any assumed arbitrary small displacement delta r bar away from this natural position of the equilibrium, but which is consistent with the system constraints, will be termed as the virtual displacement. That means there are certain constraints within the system. You give this imaginary displacement or hypothetical displacement in your mind. That displacement you assign it to your particle, but while that displacement you will be assigning, please keep it in mind, whatever constraints this particle was there under those constraints. So your displacement should satisfy all those constraints. What does that mean? It means, for example, if we consider this body, right? You see, the body is constrained to be in contact with this surface. So if I think of any imaginary or hypothetical displacement of this body, it should satisfy the constraint conditions. It means I just cannot give any displacement which will violate this constraint. That means which will violate the condition that the body is making a solid contact with this surface. So therefore, I cannot give a displacement which is vertically upward, because vertically upward displacement or a displacement which will make some angle with respect to this direction, I cannot do that displacement in that way. I have to satisfy the condition. And what is the satisfaction condition? The condition is that the normal vector to this surface and the displacement vector for this particle, any displacement which will satisfy the condition of constraint, it will satisfy this perpendicularity condition. What I mean to say, that this displacement will be always tangential to this surface. So what I mean to say is that the normal vector to this surface dot the displacement vector should be 0. So that is what is called as the condition of constraint, which is existing over here. So therefore, if I satisfy this condition of constraint, what is the condition of constraint I am saying? The normal vector to this surface, correct? And the displacement vector, they should be orthogonal to each other, or stated in other words, the dot product of this normal vector and this displacement vector, that should be equal to 0. So this is actually your constraint condition. So your displacement, your hypothetical displacement, it may be hypothetical, it may not be real, but that hypothetical displacement should satisfy this condition of constraint. That means it cannot be arbitrary in that. So it can be arbitrary in the sense as long as it satisfies all the constraint conditions. So therefore, this kind of, the displacement, we refer it to be the virtual displacement. The term
এখানটা একবার রিপিট করবেন?
কোনটা রিপিট করব বলো?
লাস্ট কনস্ট্যান্টের
ওই যে কনস্ট্যান্টটা কি বললাম? কনস্ট্যান্টটা বললাম যে if the constraint is such that you cannot give the displacement which is having an angle with this surface, তাই না? তাহলে তো কি হবে? This body will lose contact with this surface. So it has to always stay contact with this surface. So it means that the displacement that this particle will have must be tangential to this surface. Or in other words, the normal vector to this surface, and the displacement vector, they should be orthogonal to each other. Putting it in mathematical terms, the constraint condition is expressed by the vector equation that unit normal vector dot, or the normal vector, whatever, normal vector to this surface dot this displacement vector, that should be equal to 0. So your displacement can be arbitrary, but it has to satisfy this condition. So if it violates this condition of constraint, then we cannot consider it to be a consistent, the displacement which is consistent with the constraint. So you have to remember, therefore, that your virtual displacement can be virtual. That means it can be any arbitrary displacement, any arbitrary but small displacement. You need to remember that it should be very small. So it is mathematically small. So mathematically speaking, my virtual displacement will be a small quantity, differentially small quantity, we should say. In more mathematical way, it should be differentially small quantity, and it must satisfy all the physical constraints that the particle was satisfying. So therefore, if all these criteria are satisfied, then we call that displacement as to be the virtual displacement. Now we must explain this term, why it is called virtual, why not it is real. The term virtual is used to indicate that the displacement does not really exist. So this is what is, the thing. It does not really exist, but it occurs in engineer's mind. It is said that it is not really taking place in the real world, right? But it is occurring within your mind frame. You are imagining in a virtual frame of mind that this displacement is taking place. But in reality, it is not so. So it does not really exist, but only is assumed to exist so that we may compare various possible equilibrium positions to determine the correct one. So essentially, what it means, therefore, this will be considered as to be a displacement that is not real, rather it is imaginary, rather it is hypothetical, rather we should say that it takes place within the virtual reference frame of mind. Then the work done, virtual work done, we should say now we must differentiate, I must distinguish between the real work and the virtual work. So in real work, your displacement is real, your force is real. In virtual work, your force is real, but your displacements are unreal, or so to say imaginary, or so to say hypothetical, or so to say virtual. So you can therefore say, you can see that to differentiate between the real displacement and the virtual displacement, we use the symbol curl delta. So you see, this is curl delta r bar. So you see, this is delta r bar. Everything is same. That means instead of del, you could have used d. As soon as you will be using d, then it will become real. That means du equal to f bar dot dr bar, and the corresponding virtual equation will be this. Mathematically speaking, now this is very important. Mathematically speaking, there is no difference between your real differential equation and the virtual differential equation. Correct? Mathematically, it is no difference is there. That means what you can do, you can imagine it in this way. You can say that, okay, I know that the differential work done is given by du equal to f bar dot dr bar. Correct? This is what we say all the time when we solve the work energy problem. We always write our differential work done by this equation. Now, writing this differential work done, you can now write in this way. Now, rewriting the above equation in the virtual frame, the corresponding equation will be delta u is equal to f bar dot delta r bar. And this dr bar and delta r bar, there is no, basic difference. Suppose, for example, let us consider a displacement. Let us write it in this way. Suppose we open up this mathematical form. Suppose we see that the particle displacement is expressed by x is equal to a cos theta, correct? And here a is constant. That means you cannot change your a. Now, if I want to see, suppose this is representing some displacement, right? X is equal to a cos theta is representing some displacement of the particle. Now, in this equation, my a is constant. I cannot change this a, but I can change theta, and this change of theta is virtual in nature. So, what will be the virtual change of this x then? We can therefore say that you just first mentally write, I mean to say this equation is redundant, but to get accustomed initially, you can write it like this. First, you take its real differential. So real differential means this is the real change in x. So that is equal to minus a sine theta, correct? So that is what? Minus a sine theta d theta, correct? This is what you can write, that if it is a real kind of situation. Now, you just put it within bracket. I mean to say this occurs, this you write mentally. Don't write it physically, write it mentally. Then if somebody is saying that if x is equal to a cos theta where a is constant, then what will be the virtual change of x? Then we can write changing this d to del, we can write it like this. That is, it is equal to del, sorry, this is del x, sorry, it is here. So it will be, this is del x, that is equal to minus a, this is sine theta, whatever you are having, just put it here, sine theta. Then this d has to be replaced by the virtual change of angle. So it is minus del, no, this is minus del theta. So this is what is called. So I just now delete this intermediate step. So if x is equal to a cos theta, then the corresponding virtual change of x when a is constant is being given by delta x is equal to minus a sine theta into delta theta. This is how mathematically a virtual displacement will be treated, correct? So if I can have this displacement, then its virtual change is being given by this particular, the way we can write it. Now, I have used the virtual work done by the force. Similarly, we have just now seen that for a rigid body, not only you will be having forces, but also you will be having moments acting on it. And just now we have shown that when calculating the work done by the moment, we can use this equation. This is the differential work done by the moment, something like this. So you see therefore that the corresponding virtual work by the moment will be expressed by how much? Now that is, given by delta u equal to m times delta theta. So this is how you can calculate the virtual work done by the moment, correct? So this is how we can do it like this. So it is written here. You see here, this consideration is same. A line ta poro. This consideration is same mathematically as which permits us to neglect the product dx dy and writing dA equal to y dx for the element area under the curve y equal to f of x. Oh na, আমি এটা বোধহয় অন্য জিনিসটা মিন করছি, সরি এটা না, আমি যেটা বলতে চাইছি যে how to calculate this virtual change in thing. The virtual change will be ordinarily treated in this manner, মানে আমি মনে মনে এটাকে ডিফারেন্সিয়েট করব, but we will not write that differentiation because d will be always standing for representing something real, and del in solid mechanics always stands for representing virtual. সুতরাং তুমি যেরকম থার্মোডাইনামিক্সে you know that the work function, then the point function, in that case you see these the path function and the point function, এইগুলো বোঝানোর জন্য we generally use in thermodynamics the symbol d and delta, correct? So in solid mechanics we do not use that delta W, আমরা কিন্তু thermodynamics এ যদি work equation লিখি, then I should have written delta W equal to something, but we never write the work equation, মানে আমরা এখানে W লিখছি না, আমরা U লিখছি, তাহলে আমরা কিন্তু ওখানে ডেল্টা ইউজ করছি না। why? Because delta is in solid mechanics will always reserved to represent something which is virtual in nature, right? So this is the thing that we generally have from here. So this is how we can consider the whole situation. Now let us very quickly see that we can, represent the case of the equilibrium. So let us say the equilibrium. Let us suppose that this is the particle which is with several springs which may represent certain supports under the action of the different forces which are acting on this particle. Let's say this particle is initially in equilibrium. Now let us give this particle an arbitrary displacement delta r bar like this. The particle is brought from this position to this position, correct? So it is delta r bar is this, right? And while I am doing this displacement, please keep in mind all these forces will have their magnitudes constant. কেন এই কথাটা বললাম? Suppose if this displacement would have been a real displacement, in case of the real displacement, what would happen? Now these springs will change their length, and therefore all the forces which are acting on the particle at this configuration will not be the same if the particle is brought to some configuration over here, তাই না? তার কারণ the springs will be displaced in different amounts, and therefore here all the initial forces which are acting on this particle in this configuration will get changed. But in virtual displacement, although I have this particle has suffered a displacement like this, I do not change these forces. So all these forces will remain the same as it was there in the original configuration. So this is the difference between the real displacement and the virtual displacement. This you need to very carefully, you need to master this concept, that although I am having some kind of displacement here for the particle, and associated with this displacement all the lengths of the springs will get changed, but in reality, in case of virtual displacement, we will consider all these forces to be constant as they were in the initial configuration. So if I bring this particle satisfying all the constraint conditions, I do not know what are the conditions, but let us assume that this delta r bar, which is a very small displacement, which is, virtual displacement should be very small, it is arbitrary, but it satisfies all the necessary constraint conditions. So if assuming this, I get the displacement here, then the corresponding virtual work done by all the forces will be given by, this will be the equation F1 bar dot, because I said that all forces were remaining constant, so their magnitudes will be the original magnitudes and can be written like this. Now you see, therefore we can express this summation F bar in terms of its scalar components and can write it, this delta r bar, that means this vector equation is expanded into the scalar format, and in the expanded form, this will be the equation. Now if this particle is originally in equilibrium, then what it means? It means your sigma F bar, that means the vector sum of all these forces were equal to a null vector, correct? Since your particle was initially in equilibrium, we are assuming that this particle is initially in equilibrium. So it therefore essentially shows that your particle, since it is essentially originally in equilibrium, I have the vector sum of all these forces as shown by its free body diagram is equal to null, and it means therefore that sigma fx equal to 0, sigma fy equal to 0, and sigma fz equal to 0. So quite easily, therefore, I can see from here that this will be basically this result. I mean to say the virtual work done by the the forces here associated is equal to 0. So this virtual work is equal to 0 for a particle which is initially in equilibrium is considered to be an alternative method of the condition of static equilibrium of a body. So therefore, I can therefore say that if the particle, if this here we have considered it to be a particle, so I can state first the theorem for the virtual work for a single particle, and the theorem may run like this. What is the statement of the theorem? The theorem may run like this, that if a particle under the action of several forces is initially in equilibrium, if a particle under the action of several forces is initially in equilibrium, then the virtual work done by these forces corresponding to, then the virtual work done by these forces corresponding to a virtual displacement, within bracket of virtual displacement you should write it is arbitrary, small, differentially small, and satisfying all the conditions of the constraints, within bracket closed. So these are your characteristics of your virtual displacement. 3 characteristics. 1, it is arbitrary. Second, it is differentially small. And third, that it satisfies all the necessary constraint conditions. So if the particle is originally in equilibrium, I can say that the virtual work done by these forces should be equal to 0. Tahole, we can use this concept of this virtual work to express the condition of the static equilibrium for a particle. Amra jani ki je if I want to say solve the statics of a body, then I need to find out, draw the free body diagram, find out all the forces, sum them up to 0 and solve your problem. This is what basically the problem of statics is. But you can do the force approach. This is the force approach with which we are normally very much accustomed to. But the alternative pathway to approach the same problem for static equilibrium can be that you apply the principle of virtual work and say that if your particle is originally in equilibrium, then it says by the principle of virtual work, then the virtual work done should be equal to, by these forces, should be equal to 0 corresponding to any virtual displacement consistent with the constraint for the particle. Correct? So this is our, the starting theorem with which we will start. And please note that this starting theorem refers to a particle. Now we consider from particle to a rigid body. So if this concept of particle, now you see it's a single particle, you may think of now several particles. The several particles will form a rigid body under the condition that the interparticle distance between any 2 particles is going to be constant. So if I extend this concept from a single particle to a collection of particles, or so to say, for a rigid body, then we can find that the virtual work done by all these external forces will be equal to 0. So you see, this is an example. That example is shown over here. Let us suppose that this is a rigid body, and this rigid body, you see here, it is a plate. The plate is subjected to a force like this. The body is hinged over here and it is roller supported here. So we need to find, say, an external force P is applied over here like this, and I need to find out the roller reaction from here. So what I do, therefore, I just give, this body is hinged at this point O. So I just give a mental displacement. That means I give a rotation consistent with the constraint with respect to this pivot point. Then what will happen? This roller support will undergo a vertical displacement How much is that displacement? It will be b d theta, and this one will suffer, it is vertically up, and this one will have a leftward movement. How much is this leftward movement? It will be a delta theta, where delta theta is the virtual rotation with respect to point O. Is that okay? Then the virtual work done by all these forces. First of all, note that the pivot reactions, since it is immovable, the pivot reaction forces do not suffer any kind of displacement. Correct? So therefore, the work done by these pivot reactions here at this point will be 0. So the work done by the roller reaction will be how much? It is positive because your force is acting up and your displacement is also up. So it is RB delta theta, and the work done by this is negative because this is displacement is towards left while your force is acting towards right. So the total work done by this system will be RB delta theta minus PA delta theta, and this total work should be equal to 0 if this system is originally in equilibrium. So it means that for equilibrium, we can say that minus PA delta theta plus, minus PA delta theta plus RB delta theta equal to 0. Now, since your delta theta is arbitrary, it cannot be 0. So cancelling this delta theta, cancelling means you have to write the reason why you can cancel this delta theta. Because your delta theta is arbitrary and it is not equal to 0, I can therefore say, Acha, 1 minute, I just take a break. I have to attend an important call and I will come back to you. Okay, please hold on. আচ্ছা Hello, sorry. Let us, we were, the important phone came, so I had to attend that call. Now, moving back to where we were, তাহলে আমরা যদি আমরা ফেরত যাই এই পার্টিকুলার প্রবলেমটার ক্ষেত্রে, which is basically a rigid body, and our objective is that for this rigid body, if I apply this force at this point P, I like to find out what should be the roller reaction, and the body is for equilibrium, we need to find it out. So as I told you that this is a hinge point, so I consider this virtual displacement. So I mentally rotate this body. So all that is done is mentally done, because you see this kind of, the movement is never possible. How can it is never possible? Because you see this point cannot move up, right? It cannot go down also, because this is a rigid kind of support, so it cannot even go down as well. But mentally everything is possible. Everything is possible. Every displacement field is possible. Only thing that we need to see that it should satisfy the constraint condition. So what is the constraint condition here, you may ask? The constraint condition is that since you are rotating this body with respect to this point O, the hinge point, you see this displacement at this end, whose magnitude I can consider is to be B delta theta, where delta theta is that virtual angular displacement or angular rotation in the counterclockwise direction that we have assumed. One can assume the clockwise direction as well, no problem, because you know that it is all are virtual. So in reality you may think that it cannot go up or it cannot go down, but okay, just forget it. Just forget it and consider any kind of arbitrary displacement here. But there is a very big but, that this arbitrary displacement need to satisfy the boundary conditions, or sorry, the constraint conditions. So what is that constraint? That this rigid body is pivoted here. So all angular rotations will be done with respect to this pivot point, correct? So at this pivot point, therefore, if I give this, then the displacement will be upward for this. So it will be, say, if I rotate it in the anti-clockwise direction. Had I rotated it in the clockwise direction, then it would have been in the downward direction, correct? So you see, therefore, for this vertically upward displacement, you see that your displacement is B delta theta, and R into B delta theta will represent therefore the virtual work done by this roller reaction. Exactly in a similar manner, I can find out the virtual work done by this force P, which will be equal to minus PA delta theta. This minus sign is occurring, as I have already explained to you, that because of that constraint condition, the displacement of this point is A delta theta perpendicular to this direction, right? That means it is parallel to this force. This is the constraint condition. And this displacement is negative, because if I rotate it in the upward, this should move in the leftward direction. This is the constraint. This is the constraint, that if it is up, then it should be left. That if it is down, then it should be right. That means in no way, if it is up, then it can be considered as right? Because then it will violate the constraint, correct? So the constraint means essentially the geometry of the constraint of the problem. What is the problem geometry? You have to think of the geometry of your system, and from that geometry the constraint will automatically evolve out. So as a result, we can say this is the total expression for your virtual displacement, virtual work. And since by virtual work theorem, for equilibrium this must be 0. Since your delta theta is completely arbitrary, you cannot take this to be 0, because then you can say that the delta theta can be also 0. You can argue like that, but the argument will be null and void, because your delta theta is arbitrary and it cannot be 0. So this delta theta, you just set it out, cancel it out, and then you will be left out with this expression, that is PA minus RB, that will be equal to 0. So from here you can directly find out capital R equal to how much. So you see, therefore, this is basically nothing. If you look at this problem, this is nothing but the moment equation with respect to point 2. Then some of you may be thinking, then what is the very good point, of applying the virtual world? I could have straight away taken the moment of all these forces with respect to point 2 and could have very easily achieved this ultimate result with one stroke of pen. Then why the hell that I need to study the virtual world and need to apply this virtual world to this problem? The answer to this question is, okay, you have to keep your patience. In reality, the virtual work method, which I stated that it is an alternative pathway to actually, express your condition of equilibrium. This is an alternative pathway of writing your equilibrium condition. But this alternative pathway does not earn any extra interest. If the body is a single body, if it is a single particle, or if the rigid body is a single body. Okay, I will not gather any extra advantage or extra incentive of expressing this virtual work and using this virtual work to solve my problem. So where lies the honey? Where lies the beauty of this method? Now, yes, this is truly applicable when we have multiple connected system of bodies, or which is known as multi-body mechanics. In case of multi-body mechanics, where several bodies are interrelated or interlinked with each other to form a kind of structure or a kind of mechanism, there the principle of virtual work really finds its presence very prominent. And in that case, in a very effective manner, we can actually solve our problem without dismembering different elements of that multi-body system. For example, if you look at this, this configuration, in this configuration, there are two bodies. One is this link, another is this link. You see, these two links are connected here, and this roller, other link is connected to this roller, and it is constrained to move in this vertical direction. And this link system, you can say this is to be a mechanism. This mechanism is subjected to several forces, external forces, which are acting like this, correct? So in this case, if someone wants to know for equilibrium, if I am to keep the whole thing in equilibrium, for example, I am pushing this force P, then what will happen? If you see, in absence of F, because of this application of this force P, this will try to collapse down. So in order to prevent it from collapsing in the downward direction, what you do, you put a force in this direction. Or put it in another way, in absence of P, if you apply this force F, then it will try to push entire system in the upward direction. To keep it in equilibrium or to hold it in equilibrium configuration, you need to have some force P which is acting in this direction. So what is the good relationship between these two forces such that for a given geometry, this entire system can be kept in equilibrium? Now, in order to solve this problem, if it is a problem of statics, what you need to do, I will invite you to solve this problem by your conventional methods. What you need to do is to dismember all these members, show all your free body diagrams, then write all your equations of equilibrium, and then eliminate all the unwanted unknowns from your equations to establish a relationship between P and F. Probably for solving this problem, you will require a full page algebra in order to solve this system. But using this principle of virtual work without dismembering anything, without dismembering any member, using the principle of virtual work, this problem can be solved just by one stroke of line. So there lies the beauty. The problem of this type, there lies the beauty. What is the basic thing for this problem? How this problem gets differentiated from this system to that system? It is here all the single bodies were present. But in this case, you see, there are multiple bodies interconnected with each other. There can be other members as well to your system. So it becomes a plethora of bodies, or an assemble of bodies. It can be there. And for such multiple bodies, you need to write your equations very, very, judiciously, very elegantly. You can solve your problem. Now that basically, we will be going to discuss in our next session. Since today we will have just one period class, and I already overshoot the period by 6 minutes. So I will be stopping here today, but like to continue in tomorrow's class, which I remind you to be at 10 a.m. So that will be a 2-hour long class, and that 2-hour long class we like to throw some more light on this theory of virtual work. And you need to understand this basic theory of virtual work very vividly in your mind, so that you can now apply these principles in the problems. We will, of course, discuss the applications of this problem, of this method, by means of a good collection of problems. But you need to remember, there will be two basic, applications, area of applications. One is the virtual work applied to the problem of statics, and that too statics of multiple bodies, multiple connected bodies, right? There we will be basically applying this principle of virtual work. Then we will be using this concept of virtual work to a limited area of dynamics as well. So there will be basically twofold, system. First, we will discuss the whole situation for the static equilibrium situation, and then we will extend ourselves to the discussion of the problems to the dynamics, area of dynamics. So that we will gradually take up, one by one. So this is what we will be going to study in our next session. ঠিক আছে? So let us stop here today. And up till now, do you have any questions? Feel free to ask me.
Sir, how do I identify the system constraints? Like the system constraints will be the actual constraints, or it will also be
actually your question is that will I just cannot give you in one sentence how you can see your system constraints. This, as I told you, system constraints very much depend upon the geometry of your problem. For example, in the present problem that we have discussed just now, say this problem, correct? So in this problem, how you are going to define the geometry of the system, that your system is capable of rotating with respect to this point. So as it is capable of rotating with respect to this point, this end of the body will have that you see that here we have a vertical displacement here, the magnitude of which is b delta theta, and this end will have a leftward displacement that is a delta theta. So আমি কি বলেছি দেখো, যদি এটা আপওয়ার্ড হয় তাহলে এটাকে বাঁ দিকে থাকতেই হবে। If it is downward, হ্যাঁ
মানে স্লাইডটা দেখতে পাচ্ছি না।
কোন স্লাইডটা? ও, আমি প্রেজেন্টেশনটা কি বন্ধ করে দিয়েছি? ও সরি
দেখা যাচ্ছে তো।
সরি না, স্টপ প্রেজেন্টিং তো নয়, প্রেজেন্টেশন তো চালু আছে।
আচ্ছা, সেটাই বলছি, আপনার দেখা যাচ্ছে স্ক্রিন দেখা যাচ্ছে।
তাহলে ওর মনে হয় ইন্টারনেট কানেকশনে কোনো প্রবলেম আছে।
এই ছেলেটার গন্ডগোল হচ্ছে। শ্রাবণ, তুমি দেখাও শিগগিরই তোমার কম্পিউটার।
কি প্রবলেম হচ্ছে?
হ্যাঁ, আমি না, আমারও হতে পারে, আমিও মাঝে মাঝে ভুল করে ফেলি যে স্ক্রিন অফ করে দিয়েছি হয়তো। আচ্ছা, তাহলে দেখো what I was saying কি that শ্রাবণ কম্পিউটার কের একটা ভালো দেখে অনলাইন ক্লাস চালু আছে এখন, কিচ্ছু করার নেই, আমাদের করতেই হবে। সো ইউ সি দ্যাট দিস ভার্টিক্যাল, আমি এখানে সিস্টেম কনস্ট্রেন্ট বলতে কি বোঝাচ্ছি দেখো, ইফ দিস মুভস ইন দি আপওয়ার্ড ডিরেকশন দেন দিস হ্যাজ টু মুভ টুয়ার্ডস লেফট। কেউ যদি বলে যে আমি এটাকে আপওয়ার্ড মুভ করাবো আর এটাকে রাইটওয়ার্ড মুভ করাবো, তাহলে কিন্তু জিনিসটা হবে না। সো ইট ইজ কনসিস্টেন্ট উইথ দি কনস্ট্রেন্ট অফ দ্য জিওমেট্রি অফ দি প্রবলেম। ঠিক আছে, তাহলে এইখানে যে কনস্ট্রেন্ট কন্ডিশনটা হলো সেটা কিন্তু আবার এখানে যে আসবে তার কিন্তু কোনো মানে নেই। এখানে যেরকম করতে গেলে কি করতে হবে, ইফ উই অ্যাজিউম দ্যাট দিস ইজ ইন দি সেম ভার্টিক্যাল লাইন, আই মিন টু সে ও এন্ড বি ইজ ইন দি সেম ভার্টিক্যাল লাইন, যদি ধরে নিই তাহলে জিওমেট্রিটা অনেক সিম্পল হবে। সে দিস লেংথ OA ইজ A, কারেক্ট, এন্ড দিস লেংথ ইজ B, রাইট। AB OA হচ্ছে A আর AB হচ্ছে B, বা তুমি ধরে নিতে পারো যে আচ্ছা ঠিক আছে, OA ইজ ইকুয়াল টু A আর OB ইকুয়াল টু B, এটা আমি ধরে নিলাম। খাতায় তুমি যদি দেখো, আর আমি যদি মনে করি সাপোজ দিস F ইজ অ্যাপ্লাইড রাইট অ্যাট দি মিড পয়েন্ট অফ দি সেকশন OA, ঠিক আছে, একদম মিড পয়েন্টে রয়েছে। ফর সিম্পলিসিটি, if I assume that the force P is also applied at the midpoint of AB, নাই হতে পারে, এটা এরকম একটা আরবিট্রারি ডিসটেন্সেও থাকতে পারে। তো লেটস সে ফর সিম্পলিসিটি আমি ধরে নিলাম যে পিটা হচ্ছে AB মিডল পয়েন্টে কাজ করছে, মানে অ্যাজ ইফ এটা যেন তার একটা ওয়েটের মতো আর কি। এন্ড হিয়ার ও এর উপরে মিডল পয়েন্টে দ্য ফোর্স F কাজ করছে, এন্ড দি ওয়েট পার্টস অফ দি সিস্টেম আর নেগলিজেবলি স্মল, এর নিজস্ব কোনো ওজন নেই। সাপোজ এটা যদি আমার প্রবলেম হয়, তাহলে আমার সিস্টেম কনসিডারেশন কি হবে, কনস্ট্রেন্ট কি হবে না, I can therefore say, if you see this, I can consider the angle that this member OA is making with the horizontal. Let's say this angle we call it as theta, correct? আর এই AB যে লাইনটা, এই AB লাইনটা ভার্টিক্যাল লাইনের রেসপেক্টে বা হরাইজন্টাল লাইনের রেসপেক্টেও ধরতে পারো। লেটস সে ভার্টিক্যাল লাইনের রেসপেক্টে, মানে OB এর রেসপেক্টে AB মনে করো ফাই অ্যাঙ্গেলে রয়েছে। সো ওয়ান ইজ দিস থিটা অ্যাঙ্গেল, অ্যানাদার ইজ দিস ফাই অ্যাঙ্গেল। তাহলে তোমার সিস্টেম কনস্ট্রেন্ট কি দাঁড়াচ্ছে? প্রথম কথা দেখো, এখানে ইউ রিকোয়ার টু অ্যাঙ্গেলস, ওয়ান ইজ থিটা, অ্যানাদার ইজ ফাই, কারেক্ট, টু ডিফাইন ইউর জিওমেট্রি। কিন্তু দেয়ার ইজ এ রিলেশনশিপ বিটুইন থিটা অ্যান্ড ফাই। কিরকম রিলেশনশিপ দেখো তুমি, since I said that O and B is in the same vertical, along the same vertical, আমরা আমাদের আলোচনার সুবিধার জন্য ধরে নিচ্ছি যে ইট ইজ লাইন অ্যালং দি সেম লাইন, তাহলে অবভিয়াসলি আমার এই যে ডিসটেন্সটা, দ্যাট উইল বি হাউ মাচ, দ্যাট উইল বি A cos থিটা, এন্ড হাউ মাচ ইজ দিস ডিসটেন্স, এখান থেকে এইটুকু, এই যে এখান থেকে এইটুকু, A থেকে B এর হরাইজন্টাল ডিসটেন্স, হাউ মাচ ইট উইল বি না, দ্যাট উইল বি B sin phi। তাহলে আমি একটা জিনিস লিখতে পারি এখান থেকে প্রথমেই, সো আই ক্যান রাইট ফ্রম হিয়ার দ্যাট A sin থিটা, তাহলে আমরা এরকম লিখি, দেখো অল আর কনস্ট্রেন্টস, মানে আমি ওইটাই তোমার শিব যে প্রশ্নটা করেছে, দ্যাট ইজ একদম মোক্ষম প্রশ্ন, যে কি করে আমি কনস্ট্রেন্ট চিনবো, সেটা কিন্তু হচ্ছে তোমাকে প্রবলেম দেখে দেখে আইডেন্টিফাই করতে হবে। সরি, দিস উইল বি A cos থিটা, A cos থিটা ইজ ইকুয়াল টু হচ্ছে B sin phi, তাই তো, আমরা তাই বললাম, B, আমরা সেই রকম অ্যাঙ্গেল গুলোকে সেইভাবেই দেখেছি। সো ইট ইজ B sin phi। তাহলে এটা হচ্ছে একটা কনস্ট্রেন্ট কন্ডিশন আমি পেলাম এখানে, যে এই ডিসটেন্সটা আমার দুটো হরাইজন্টাল জায়গা থেকেই সমান আসবে at any angle theta and any angle phi, ঠিক আছে। তাহলে এটা হয়ে গেল, এই গল্পটা হয়ে গেল। ওয়ান্স দিস ইজ ডান, আমরা কিন্তু এখান থেকে সরাসরি এখান থেকে ফর ডিফারেন্স, মানে ভার্চুয়াল চেঞ্জ অফ দি অ্যাঙ্গেল থিটা এন্ড ভার্চুয়াল চেঞ্জ অফ দি অ্যাঙ্গেল ফাই, আমরা সরাসরি এখান থেকে লিখতে পারি, কি লিখতে পারি না, আমরা লিখতে পারি মাইনাস A সাইন, দেখো কি লিখছি খুব ভালো করে খেয়াল করো, মাইনাস A সাইন, সরি, মাইনাস A sin theta delta theta. So we can write delta theta should be equal to, কি লিখছি না, it will be B cos b cos phi ডেল্টা ফাই। কি করলাম, দুদিকটাকে ডিফারেন্সিয়েট করলাম, কিন্তু ডিফারেন্সিয়েট কথাটা লিখলাম না, মনে মনে ডিফারেন্সিয়েট করছি, লিখছি ভার্চুয়াল। সো দিস ইজ দি কনস্ট্রেন্ট কন্ডিশন, দ্যাট মিন্স ডেল্টা থিটা এন্ড ডেল্টা ফাই মাস্ট স্যাটিসফাই দিস কন্ডিশন, কারেক্ট? আচ্ছা, নাও ইউ সি হিয়ার, দেখো তোমার এখানে এই যে ফোর্স এফ, এবারে আমাদের ভার্চুয়াল ওয়ার্ক ক্যালকুলেট করতে হবে। তাহলে আমরা কি করি, এখানে ফ্রি বডি ডায়াগ্রামটা ঝপ করে এঁকে ফেলি। ইন দি কেস অফ দি ফ্রি বডি ডায়াগ্রাম, আই ফাইন্ড দ্যাট the pivot reactions will not contribute anything because this is immovable, আর এখানে যে নরমাল রিঅ্যাকশন কাজ করবে because it is roller supported, that will be always perpendicular to the movement। সুতরাং এই রিঅ্যাকশন ফোর্স আর এই পিভট রিঅ্যাকশন ফোর্স, they are not contributing anything to my work equation. So this is what is active force diagram. Active force diagram only takes care of those forces which contribute into my work equation. তাহলে অ্যাক্টিভ ফোর্সে কেবল আছে হচ্ছে এফ আর পি, কারেক্ট? তাহলে দেখো এফ হরাইজন্টালি কাজ করছে, তাহলে লেট আস সি হাউ মাচ ইজ দি হরাইজন্টাল পজিশন অফ দি পয়েন্ট। যে পয়েন্টটা এখানে কাজ করছে সেই পয়েন্টের হরাইজন্টাল ডিসটেন্সটা কত? So if I draw the y-axis and x-axis in this way, I can see the horizontal coordinate of this or distance of this point for this angle theta. কত আসবে না, সেটা হচ্ছে a/2 cos theta. So we can therefore say, কেউ একটা ঢুকলো বোধহয় ক্লাসে, দেখো শিবনাথ রানা। কি হলো রে, তুই বেরিয়ে গেছিলি কেন?
স্যার বলছেন, স্যার একটা আমার হঠাৎ কল এসেছিল, তারপরে আমি ওটা অফ করে দিলাম, তারপরে আমার ইন্টারনেট অফ হয়ে গেল, তারপরে আমি আর কানেক্ট করতেই পারছি না আর কোনো কিছু।
এ বাবা, তাহলে দেখো তোমার প্রশ্নটাই কিন্তু আমি উত্তর করছিলাম। তাহলে দেখো এখানে ওই জন্য ক্লাসে কখনো কল নেবে না, আমাকে নিতে হয়, কারণ আমার অনেক ইম্পর্টেন্ট কল আসে।
কল নিইনি, মানে হচ্ছে কলটা অফ করতে গেছিলাম, অফ করতে গিয়ে তারপর দেখি আমার ইন্টারনেট কানেকশনই চলে গেছে।
হ্যাঁ, অনেক সময় হয়। তাহলে দেখো যে আমার এই হরাইজন্টাল ডিসটেন্সটা এই পয়েন্টটার কত আসছে না, দ্যাট উইল বি ইকুয়াল টু a/2 cos থিটা। তাহলে আমি এখানে থেকে দেখো লিখতে পারি দিস ইজ a/2। তাহলে আমি জাস্ট লিখছি তোমার এখানে সুবিধার জন্য ঝপাঝপ, হ্যাঁ তাড়াতাড়ি করে করছি। দিস ইজ a/2 cos থিটা, a/2 cos থিটা, সেটা হচ্ছে এই লোকটার পজিশন, দা পয়েন্ট, এখানে পজিশন। আর এই লোকটার পজিশন কোথায়, আমি ধরে নিয়েছি যে এটা মিডল পয়েন্টে কাজ করছে এবি, তাহলে এই লোকটার পজিশন কোথায় না, উই ক্যান দেয়ারফর সে দ্যাট ইট উইল বি হাউ মাচ না, দ্যাট ইজ ইকুয়াল টু b/2 cos phi। b/2 cos phi হচ্ছে এই এখান থেকে, মানে পয়েন্ট এ থেকে এটার উচ্চতা, কিন্তু পয়েন্ট এ আবার অনেক উঁচুতে বসে আছে, তার মানে অ্যাকচুয়ালি এই যে পয়েন্টটা তার কোঅর্ডিনেট কত আসছে, the point where the force P is acting, তার কোঅর্ডিনেট কত আসছে না, we can therefore say যে এর কোঅর্ডিনেট আসছে হচ্ছে b/2, let's see first, b/2, it is b/2 cos phi, b/2 cos of phi, cos of phi, কোথায় গেলি রে এইটা, প্লাস হচ্ছে গিয়ে কত না a sin phi, এই সরি a sin theta, সরি a sin theta। দেখো বুঝতে পারলে কিনা, নিজের খাতায় ছবি এঁকে এটা বোঝার চেষ্টা করো। তার কারণ হচ্ছে কি, দিস অ্যাঙ্গেল ইজ থিটা, তাহলে এইটুকু হচ্ছে a sin theta, আর এখান থেকে এইটুকু হচ্ছে b/2 cos phi। So I get this is the, these are the positions, horizontal position and these are the vertical positions। মানে এটা হচ্ছে x is equal to, this is x is equal to এটা, আর এটা হচ্ছে y is equal to, মানে যে পয়েন্টে আমার ফোর্স গুলো কাজ করছে তাদের কোঅর্ডিনেটটা আমি লিখে ফেললাম। তাহলে এটার যদি ভার্চুয়াল চেঞ্জ করি তাহলে কি হবে, তাহলে এটার ভার্চুয়াল চেঞ্জ কি রকম দাঁড়াবে না, উই ক্যান সে দ্যাট এর ভার্চুয়াল চেঞ্জ হবে হচ্ছে ডেল্টা এক্স, তাহলে এটাকে আমরা লিখবো ডেল্টা এক্স ইজ ইকুয়াল টু, দিস উইল বি মাইনাস a/2 minus a/2, then it will be sin theta, আমরা এটাকে কপি করে নিতে পারি, মাইনাস sin theta delta theta, এটা হচ্ছে এটার চেঞ্জ, আর এটার চেঞ্জ কি দাঁড়াবে, সিমিলারলি এটার চেঞ্জটাকে তুমি বের করে ফেলতে পারো y এর চেঞ্জটাকে, so you can write this will be delta y, correct, so that will be equal to কি দাঁড়াবে না minus b/2 sin phi, so we can write something like this, copy paste, put a minus sign, minus b/2, this will become sin phi, correct, this will become sin phi delta phi, এটাকে নিয়ে এসো এখান থেকে, minus sin phi delta phi plus কি হচ্ছে না এটা হচ্ছে a cos theta, so we can say this will be a cos theta delta theta, so just take this delta theta here, copy and paste it. So these are therefore delta x and delta y, virtual change of the coordinates where your forces are acting. Finally এসে কি দাঁড়ালো, ভার্চুয়াল ওয়ার্ক, ভার্চুয়াল চেঞ্জ, তাহলে লেখো del capital U is equal to কি দাঁড়াচ্ছে দেখো, look at this expression, so it will be আমার x পজিটিভ কিন্তু এই দিকে, হ্যাঁ towards right, আর y পজিটিভ হচ্ছে towards up, তাহলে আমি দেখছি আমার ফোর্সটা হচ্ছে x এর নেগেটিভ ডিরেকশনে, তাহলে আমি লিখছি মাইনাস f ইনটু ডেল্টা x, মাইনাস f ইনটু ডেল্টা x বসিয়ে দাও, কারেক্ট, আর কি থাকছে না মাইনাস p, কারণ ফোর্স ডাউনওয়ার্ড আর আমার y হচ্ছে উপরের দিকে, তাহলে মাইনাস p ডেল্টা y, this must be equal to, this is the total virtual work done, and this must be equal to 0, or in other words এই মাইনাস সাইন গুলোকে তুমি হাওয়া করে দাও, তাহলে f delta x plus p delta y is equal to 0, তাহলে তুমি এখান থেকে কি পাবে, f আর p এর মধ্যে রিলেশনশিপ পাবে বিটুইন ডেল্টা x and ডেল্টা y, এই ডেল্টা x ডেল্টা y কিন্তু আমার এখানে দেখো অলরেডি বের করে রাখা আছে, তার মধ্যে আবার একটা ডেল্টা ফাই ঢুকে আছে, সেই ডেল্টা ফাইটাকে তোমাকে এলিমিনেট করতে হবে এই ইকুয়েশন দিয়ে, তাহলে আলটিমেটলি ইউজিং 1 2 3 এই তিনটে ইকুয়েশন বসিয়ে এখানে যদি তুমি বসিয়ে দাও এই ইকুয়েশনটার মধ্যে, ফাইনালি আইদার ইউ ক্যান এক্সপ্রেস দিস ইকুয়েশন আইদার ইন টার্মস অফ ডেল্টা থিটা or you can express it in terms of delta phi, দিয়ে সলভ করলে তুমি যেটা পাবে, that will be the relationship between f and p for equilibrium for this problem. I would ask you to solve this problem at your home, বাড়িতে এটা করে ফেলো, এই এখান থেকে f আর p এর রিলেশনশিপটা পেয়ে গেছো, এই ডেল্টা x টাকে এখানে বসিয়ে দাও, দেখো এখানে একটা মাইনাস সাইন আছে, আবার এখানেও একটা অর্ধেকটা মাইনাস অর্ধেকটা প্লাস আছে, তো যাই হোক ওই রকম করে এখানে বসিয়ে দাও, বসিয়ে দিয়ে ইউ উইল হ্যাভ এ রিলেশনশিপ বিটুইন ডেল্টা থিটা এন্ড ডেল্টা ফাই, আবার দেখো এখানেও একটা রিলেশনশিপ আছে ডেল্টা থিটা এন্ড ডেল্টা ফাই, তাহলে এদিকটা যেহেতু শূন্য, তুমি এখান থেকে ডেল্টা থিটা ডিভাইডেড বাই ডেল্টা ফাই কত তুমি বের করে নিতে পারো এই ইকুয়েশনের মধ্যে, এই ডেল্টা এক্স আর ডেল্টা ওয়াই গুলোকে এটার মধ্যে বসিয়ে দিলে তুমি রিলেশন ফ্রম হিয়ার ডেল্টা থিটা বাই ডেল্টা ফাই কত তুমি এখান থেকে পাবে, আবার এখান থেকেও একটা ডেল্টা থিটা বাই ডেল্টা ফাই তুমি পাবে, নাও ইকুয়েট দিস টু and then set a relationship between f and p and express your relationship যে কোনো একটা অ্যাঙ্গেল সে থিটার অ্যাঙ্গেলে থিটার টার্মসে তুমি এটাকে এক্সপ্রেস করো, always remember relationship between phi and theta is being given by this equation a cos theta equal to b sin phi, ঠিক আছে, তাহলে আলটিমেটলি তুমি এখানে দুটো ভেরিয়েবল ইউজ করেছো ডেল্টা থিটা এন্ড ডেল্টা ফাই, so apparently it looks like the system is having 2 degrees of freedom, in reality it is just only 1 degree of freedom because you have a constant relationship like this, তাহলে এইটা যে কোশ্চেনটা শিবনাথ করেছে ইনফ্যাক্ট ভার্চুয়াল ওয়ার্কের এটাই সবচাইতে কঠিন প্রশ্ন, how to write your constraint conditions, এইটি হচ্ছে ভার্চুয়াল ওয়ার্ক। তারপরে বাকিটা ইজ ভেরি সিম্পল, জাস্ট ওয়ার্ক ডান। দেখো এখানে কিছুই নেই, আমি এই যে পরপর পরপর ইকুয়েশন গুলো লিখেছি, দিস ইজ দি ফাইনাল ইকুয়েশন, কারেক্ট? তো এটার অঙ্কটার মধ্যে কিছু নেই, কিন্তু অঙ্কটার মধ্যে যেটা আছে, হাউ টু এক্সপ্রেস ইউর কনস্ট্রেন্ট রিলেশনস, দ্যাট ইজ দি মোস্ট ভাইটাল থিং for which you need to carefully see the geometry of the problem and identify your equations. We will show how more আমরা যখন প্রবলেম করব তখন সেই প্রবলেমেতেও আমরা এটা প্রত্যেকটা স্টেপে I will try to explain how we have found the constraints. কিন্তু ওই যে বললাম তোমাকে, তোমায় নিজে নিজে অঙ্ক একটু করতে হবে আমার সাথে থেকে until and unless you know use your brain and hands and minds to express the geometry of your problem, then এই ভার্চুয়াল ওয়ার্কের কিন্তু কনস্ট্রেন্ট কন্ডিশন বের করাটা কিন্তু will be a tough proposition. আমি এটার দ্বারা কিন্তু কাউকে ভয় দেখাতে চাইছি না, it is very simple, only thing you need to practice. হ্যাঁ, এই বইতেও কিছু অঙ্ক করে দেওয়া আছে এক্সাম্পলে, এখানেও এক্সাম্পলে বেশ কিছু অঙ্ক করে দিয়েছেন মেরিয়াম সাহেব। তো সেই অঙ্কগুলো ভালো করে স্টাডি করবে, এখানে যে অঙ্কগুলো আছে সেই অঙ্কগুলো ভালো করে স্টাডি করবে। অ্যাট দি সেম টাইম আমি তো বেশ কিছু অঙ্ক করেওছি তোমাকে এক্সারসাইজের থেকে, তো আই উইল শো দোজ এক্সারসাইজ প্রবলেমস এন্ড এক্সপ্লেইন দেম ডিউরিং আওয়ার ক্লাস। সো হোপফুলি ইফ ইউ ডু ইট দেন ইট উইল বি ডান। বোঝা গেল বাবু?
হ্যাঁ স্যার।
ব্যানার্জি, এতক্ষণ তুমি কোথায় ছিলে? বাইরে বেরিয়ে গেছিলে কেন শ্রাবণ?
স্যার নেটওয়ার্কটা একদম আবার পুরো।
হ্যাঁ, তুমি একটুখানি নেটওয়ার্ক উন্নত করো, তুমি তো কলকাতায় থাকো, তোমার তো প্রবলেম হওয়া উচিত নয়, একটু ভালো সিস্টেম তোমাকে জোগাড় করতে হবে একটুখানি।
স্যার মানে আমাদের এই লোকাল সেই ইয়ের নেটওয়ার্কটা মানে গন্ডগোল করে স্যার। ব্রডব্যান্ড
লোকাল নেটওয়ার্ক মানে কি? তুমি কি ফোনের নেটওয়ার্ক ব্যবহার করো না এমনি কোনো তোমার আছে?
ওয়াইফাই।
ওয়াইফাই, ও তাহলে তোমার সেই ওয়াইফাই ওয়ালাকে ধরে বকাবকি করো একটু, যে আমার তো ওয়াইফাইটা নিয়েছি তো আমি নেটফ্লিক্স দেখার জন্য নয়, আমি এটা নিয়েছি হচ্ছে অনলাইন ক্লাসের জন্য। বা সেটাই যদি আমি ঠিক করে না করতে পারি তাহলে তো মুশকিল। ঠিক আছে, তাহলে আমরা আবার আগামীকাল বসবো সকালবেলা। তো আমি তোমাদের বলবো, কালকে আমরা যদিও টাইমিংটা 10টায় রেখেছি, but I would ask you that please be there at least 10 minutes before the class, so that যদি তোমরা 10 মিনিট আগে চলে আসো ক্লাসে, মানে ধরো 9টা বাজতে 10-এ যদি 10টা বাজতে 10-এ যদি চলে আসো, then we can start from at that point. হ্যাঁ, আমরা ওখান থেকেই তাহলে স্টার্ট করি। আর যদি একটা কি দুটো হয়তো এক্সট্রা ক্লাস লাগতে পারে, না লাগার সম্ভাবনাই বেশি, হয়তো লাগতেও পারে। আমি একটু বলে রাখলাম এক্সট্রা ক্লাসের কথা, সেই রকম হলে I will talk with you and arrange an extra class to cover the theory portion so that we can get it in time. তোমাদের পরীক্ষা আমি 9 তারিখে রেখেছি, 9 তারিখে মানে বেশ অনেকটাই সময় তোমার হাতে আছে, হোপফুলি তার কনভিনিয়েন্ট টাইমেই আমি জিনিসটা শেষ করে ফেলতে পারবো।
ওকে স্যার, ওকে স্যার।
ঠিক আছে, বলো নির্নিমেষ কি বলছো?
আচ্ছা আমি ওটা ওকে স্যার বললাম।
হ্যাঁ ওকে স্যার, আচ্ছা ওকে স্যার।
আচ্ছা
হ্যাঁ বলো।